Hello, welcome back to the Algebra 2 course. This is Unit 9. The topic of this batch of lessons is basically going to be zeroing in on solving these quadratic equations. You can also call it finding the roots of these quadratic equations. But what we're going to do in this lesson is we're going to back up the truck a little bit, zoom out a little bit so that we don't forget what we're doing. And I have a computer demo that I'm going to do for you here in about 20 seconds that's going to hopefully illuminate a lot of what we're talking about before we get back to the board and write the math down. So remember, the point is when we're talking about roots of an equation, what we're really doing is we set that equation equal to 0 because those will be the points where the graph crosses the x-axis because those are the points where the function is equal to 0. The function is the y-axis, right? So if you set it equal to 0, you're finding all the points where it crosses that x-axis where the value is equal to 0. So we have lines, which are linear guys like this that only cross the x-axis in one location. We have quadratics, which look like the parabolas we've talked about. They generally cross the axis in two locations. And then we have cubics, and then we have, the higher order polynomials beyond that. And so what we're going to be doing here is covering the general idea of linear equations, quadratic, cubic, which is the power of 3, and the quartic equations, which is the power of 4. So before we get back to the board here, let's do that computer demo and I'll show you graphically what the roots of these different kinds of equations really look like. Okay, welcome back here. What we have here is a little demo that I've done here where I can show you the graphs of the different kinds of equations here. We have linear equations and the higher order polynomials beyond that. So the simplest kind of equation you can have is a horizontal line. So the graph here, it just says 3 here. That means y equals 3. That's a horizontal line that crosses at the value of y is equal to 3. Here, the line crosses at the value of y is equal to 4. You can see that this horizontal line does not cross the x-axis at all, so it doesn't have any roots. But if we make the line a little more interesting, if we put a slant to it, then here's the equation of this line, 2x plus 4. You can see the y-intercept is up here at 4, and it has a slope of 2, rise over run. That's what this means, right? And you can see that in general, when a line is slanted, it is going to cross the x-axis in one location. Now, I can play around with this line. I can bring it down like this, so the y-intercept is -3 down here. And you can see that the root here of this first order equation, see the power of x here is just a 1, so we have a first order root here, which basically means we expect to have one solution when we set this guy equal to 0, which means one crossing point. Here's the crossing point. Now, no matter what I do, even if I make the line slant the other direction, if I shift it up or down, basically move the line around, it's only going to cross the x-axis in one location. It has one root because the power of x is just a number 1. Now let's go up and I'm going to drag my slider here to make a quadratic. So this is a simple quadratic, and I can reset the rest of these guys here to kind of reset what I have here. So this is the quadratic y is equal to x squared. If I change it to make it, for instance, x squared minus 3, this is what this curve looks like. Now, the highest power of x here is a 2. That means it's a quadratic. All quadratics have a power of 2 for the highest power. And because the power is 2, that means that we have 2 roots of this equation, right? And in this case, one root is where it crosses the x-axis here, and the other root is where it crosses the axis over here. So you can see that they're mirror images. Now, as I change the graph a little bit, you can see the crossing points are in different locations, but there's still 2 roots. Now, if I change very slightly what the equation looks like, maybe make the parabola more sharp by putting a higher coefficient in front of the x squared here, it does change the shape of the curve, but we still have 2 crossing points. And with quadratics, we always expect to have 2 crossing points because the highest power of x is a 2. Just like in the case of a line, like this line right here, or any line in general, we always expect only 1 crossing point because the highest power of x is a 1 here. So let's go back up and make it a quadratic. Now you can see we have 2 crossing points. You can see there's a crossing point here, there's a crossing point here, so we have 2 roots. Now what I want to draw your attention to is, if I drag this quadratic above the x-axis so that you see how it never intersects, this quadratic never intersects the x-axis at all, that means that this function never ever has a value where it's equal to 0. So it doesn't have any real roots. But as we're going to learn here very soon when we talk about the quadratic formula, we're going to see that this quadratic equation still has 2 roots. But because we don't have any crossings on the x-axis, they're not real roots. We always have 2 roots, but we're going to turn out and see that when the graph is floating up here, we have 2 complex roots or imaginary roots. We've talked about complex numbers before. So this quadratic equation still has two roots. It's just that they're both complex, and so we can't see them on this graph of real numbers, the x and y graph here. So you see, no matter what I do, if I move this guy maybe over here, maybe shift it way up high, you see down below, once it crosses down below, we have two real roots. As I increase it, we still have two real roots. We still have two real roots. They're getting closer and closer and closer together. We have two real roots right here. Here we still have two real roots. Here's one here and here's one here. But as I pop over to the other side like this, then I have actually no real roots, but I still have two roots in total. I have two complex roots, and we're going to learn how to calculate the complex roots with the quadratic formula here very soon. All right. One more thing I'm going to say before I leave quadratics here is let's do a basic quadratic that's centered on the x-axis right here, or centered on the, like this guy, the general quadratic, like 2x squared, or you could say x squared. Notice here that as I, let me make it a simpler one. Let's make it y is equal to x squared. So here's the general y is equal to x squared graph, right? Let me drag it down below, and you can see that there's two roots, one here and one here. Now, as I move it up higher, let's go farther down. You see the roots are very far spaced apart because the thing is way below the x-axis. As I make this and shift this graph up, the roots get closer and closer and together. You see what's happening? They're getting closer. Here is -1 and +1. And as eventually I get to make the graph shift up to this point, the roots have gotten so close together that they're right on top of each other. The roots are actually right here at x is equal to 0, but there's still two of them. It's a quadratic. There has to be two roots. They're right on top of each other, and we call that a double root. So it's easy to see when you actually start down here. We have double roots, double roots, double roots, I'm sorry, not double roots. We have two roots, two roots, two roots, two roots, and so on. They're getting closer. Eventually, we still have two roots that are right on top of each other. We call that a double root. And then as we go above the x-axis, we don't have any real roots at all, no crossing points, but we still have two complex roots, which we'll learn about later. Now let's increase it to a cubic. This is what a general cubic function looks like, and I can play with it to try to make it more like a snake. It's kind of like a snaky function. And so this is what a cubic looks like, and you can see here at the highest power of x is a 3, so we expect 3 roots of this equation, 3 crossing points. So here's a crossing point of the x-axis, here's another crossing point here, and here's another one. So there's 3 roots of this equation. In general, all cubic functions are going to look like this, or they'll look like a mirror image flipped down below. In other words, it can go up and down or down and up, but it'll still mostly look like a snaky kind of function like this. And as I go and drag this guy down, interestingly, there's only one crossing here of this function here. It still looks like a snake, but we only have one root, which means one real root we can see over here. But you have to remember the highest power here is a 3. We always have to have 3 roots total. So here we have one actual crossing point, and we have 2 other roots, which you could find. We're going to learn how to solve these cubics later, and you'll find out you'll have 2 complex roots for a total of 3. 2 complex roots, and then the one real root here. As I drag the function up, we still have 2 complex roots and then the one real root over here. As I drag it up here, we have one real root here, and notice we have a double root now because the function is now touching the x-axis. And then as I go through it, now we have 3 real roots. 1, here's 2, and here's 3. And as I shift the function up, we still have 3 real roots here, 3 crossing points. And then we have, on this case, we have the function crossing here. That's a real root. We have a double root now for a total of 3 roots here. And then as the function gets shifted up, it's a little hard to see because it's shifted off the screen. That's probably better. We have now a 1 real root here on the negative side, and then we don't have any other crossing points, so the other 2 come up to make 2 more imaginary or complex roots. So the bottom line is you always have as many roots as you do the highest power, but some of them can be complex if you don't have enough crossing points in your graph. And that's what it means to get complex roots. Those are just roots that can't be displayed on a real graph like this, but the real crossing points will show up as roots as well. Now, real quickly, we're not going to go through the quartic and higher too much, but let me just show you generally what in general quartic function looks like. You can play around with it, make it look various ways. So here in general, you can see it looks like a W. So whereas the cubics look like a snake, the quartics look like a W. Of course, it could be flipped upside down to look like an M as well. But if I drag this function down here, then this Quartic equation, this one here that we have printed at the top, has two real roots because we have two crossing points, but we don't have any more actual crossing points, so the other two roots that we expect must be complex. So this graph would have two real roots and two complex roots that you can't see on this graph. As I shift it up, it's the same deal. We have two real roots and two complex. Here we have two real and two complex, but now you see the graph crosses in four locations. 1, 2, 3, and 4. So this graph has actually 4 real roots, and it doesn't have any complex roots. And as I shift it up, we have, whoops, let's go here. Here we have the same deal here. 1, 2, 3, 4 real roots and no complex roots. And as we shift, let me see if I can get it here. And I don't have the granularity. But as we go up higher above the axis, this graph, this equation, doesn't have any crossing points at all, so all 4 of these roots must be complex. So you can kind of predict from the graph how many real and how many complex roots you're going to have. Now I'm just going to fly through the rest of them because after you get to the quartics, the rest of them are just kind of hard to kind of visualize. But you can see a 5th order equation still kind of looks like a snaky function, and if you push it down like here, you can see you have now 5 crossing points. 1, 2, 3, 4, and then 5, matching the 5 roots that we expect. Here are the 5 real crossing points. If I shift this equation up, changing it slightly like this, now the roots will be 1 real root, and all 4 of the remaining to equal 5 must be complex roots. And I can do the same thing by dragging it down here. This equation has 1 real root way over here, and then all of the other 4 must be complex roots. And then in the middle, as I shift it up and down here, you can see you can have various combinations. Here I have the 5 crossing points in total. And just playing around with it more, you can make crazier, higher order things like this. Let me see if I can find something interesting. Here you have 1 crossing point, 2 crossing points, 3, 4. So I only have 4 crossing points that I can see in this function, but we know that there must be 6 roots because it's a 6th order polynomial. So we have 4 real, therefore we must have 2 complex. So if you solve and find all of the roots of this equation, then you'll find 4 crossing points, 4 real roots, and then the other 2 must be complex. And then we'll just do one more, just because I know you're curious. The 7th order, see if I can make it look interesting. So this is a 7th order polynomial. You can see the graph of it, but how many crossing points do we have? 1, 2, 3, 4, 5. We have 5 real roots, therefore the other 2 to make 7 must be complex roots. So I wanted to show you the general idea of what we were doing so that you can get an idea of what real roots are and what complex roots really represent. But what I want to do here to close is go back to the original thing. When we have our general quadratic equation, our famous f of x is equal to x squared, right? If it has 2 crossing points, that's 2 real roots. If you have no crossing points at all, that's 2 purely complex or imaginary roots that you're going to get when you solve this guy. And then right when it kisses the axis, you have 2 real roots, which we call a double root. You can see them getting closer and closer and closer together until now they're just basically right on top of each other. If I can adjust it here, right here at x is equal to 0. So now let's go back to the board and wrap it up with writing down some equations. All right, so now that we've seen the demo of how these roots really behave when we have higher and higher order polynomials, what we want to do is kind of write some of the things down to make sure you understand and have it all in one place. So the simplest kind of equation that we really have and learn about is called the linear equation. That means it's an equation of a line. And we talked about that for many hours, a long time ago. And the equation of a line looks like this. F of x is equal to ax plus b. Now, a and b can be numbers, any number. So it could be 2x plus 3, 3x minus 5, and so on. And you can think of this as the slope. Whatever this is the slope in front of this, and this is the y-intercept. And the way that we find the roots of this guy is we solve the equation ax plus b, whatever it is, equals 0. We know how to solve for x. We move b over, we divide by a. But in general, what we get, as we saw kind of in the video there, in general, the line could be horizontal with no crossing points. That's true. But in general, it's going to have 1 crossing point. In this particular case, this is x, this is f of x. The crossing point is actually right here, at this value of x right here. So this is one solution. And you could say it's like at x is equal to 2 or something. If I'm just making this up, I'm just giving you an example. As we saw in the video there's 1 crossing point. There's 1 solution because we expect 1 solution because the highest power of x is just equal to a 1. Now moving up the complexity a little bit, we have the famous quadratics. Quadratic. equations, which we're going to be using and zooming in on almost entirely in this lesson. But the quadratic equations in general look like this. All of the quadratic equations have the form ax with a power of 2 plus some number times x plus some other number. Now a, b, and c can be any value except for one exception, and that is that the value here, a cannot be equal to 0. In other words, for it to be a quadratic, you have to have you can't have 0 here, otherwise it would kill the quadratic term entirely, right? So in order to find the roots of the quadratic equation, how many crossing points you have, what you do is you take this quadratic equation you have, ax squared plus bx plus c, and you set it equal to 0. Then you factor it, or you could do completing the square like we've been doing. We're also going to learn about we will be doing actually completing the square to solve this guy. We'll also be using the quadratic formula to find out the values of x that satisfy this equation. And then the main idea is, what is the values of that equation actually represent? Well, there's a couple of different cases, and we saw some of them in the video there, in the demo there. But let me just draw a couple of cases here. If your quadratic, depending on the values of a and b and c, happens to look something like this, an upside down parabola, then there's two crossing points because you're setting the value of this equation equal to 0. So this is going to be a solution, and this is going to be a solution. There's going to be two solutions, right? So you're going to have two solutions, right? And just to kind of make things up, you could say that x would be -3 and x could be positive, 2 or something. I haven't exactly drawn it, but you see the idea. You have two positive negative value in this case. You have two actual roots. What are some other cases that you can get with quadratics? What does it actually mean, right? Well, you could have a case like this. You could have, of course, a parabola that dips below the x-axis like this. So you have two crossing points still. You have a crossing point here and a crossing point here. You still have two solutions. You have two solutions. And the values of these solutions are both positive. So it might be, for instance, x is equal to 1 and x is equal to 3. Those are two real solutions. But there are other ideas and other kind of possibilities, right? You could have, let's go over here and draw a couple of different possibilities. What if you had the parabola, as we saw in the demo there, floating kind of up above the x-axis? Well, you see, there's no crossing points. There's no values where this equation actually equals 0. All of the values of the function are all above 0. So there are no crossing points, so there are no real roots, right? So no real roots. But what we're going to find is there's still two roots of the equation. They're just both complex, which involve imaginary numbers. Now, another example of when you would have no real roots is, what if the equation kind of is down below but going upside down? So you see all of the values are negative for this function. They do not ever cross the x-axis. So again, there's no real roots here either. No real roots. Right? And then, of course, we have the one final example that we really need to talk about, which is the case that we kind of illustrated in the video here, in the demo here just a minute ago, and that is the case of the double roots, right? So what if you have the quadratic come down and just barely touch the axis, but only in one spot? It can be at a positive oriented curve like there, or it could be in a negatively oriented curve where it only touches in one spot here. In either case, there's still what we call two roots, but we call it a double root. And when I was learning this stuff the first time, the idea of a double root really confused me. Why is it a double root? Well, it's because, as I showed in the demo there, as your quadratic goes closer and closer and closer to the axis, the roots get closer and closer together. Eventually, when it's just touching the axis, there's still two roots, but they're infinitely close together. They're basically on top of each other, so they have the same exact value. X is equal to 1, and then x is equal to 1. They count twice. You still have to have two roots. So you still have two roots for this equation, 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 and even these equations have two roots, but they're both complex. And we'll learn how to find those when we continue learning how to solve these quadratics, which is what we're going to be doing mostly in this section. But this is an overview section, and I want to talk about more than quadratics. We talked about this in the demo, cubic equations. The general form of the cubic equation looks like this. F of x is some number times x to the third power plus some number, x squared, plus some number times x plus some number, right? That's f of x. That's a cubic equation. This number here needs to be something other than 0, but any of these other ones can be 0, like b, c, or d could be 0 Because, in other words, it doesn't matter what the rest of this thing is. It's a cubic if the highest power is a 3. So to figure out the roots of this guy, what you're going to be doing is you're going to solving this equation, x to the third plus bx squared plus cx plus d, and you're going to set that guy equal to 0. And we're going to learn, as we get a little farther into algebra, how to solve cubic equations. We're going to learn how to factor things out and how to separate and divide things, and we're going to figure out the roots of this guy. But graphically, what does it actually mean? We saw in the demo, in general, what it means, but I want to make sure everybody understands. Now, in general, the cubic equations, I call them these snaky functions. They go up and then down and back up. So you see there's 3 crossing points corresponding to the 3 solutions that we expect to find. So for instance, you might say that x is equal to, like, over here, -4. You may say that this root is over here at -1, and you might say that this root is at +2 or something. So there's 3 real roots here, 3 real roots for this equation, if this is what it were to look like. But there are other possibilities, which we saw over there when we did the demo there. And there's infinite possibilities, really, but you might have one that goes up like this and then snakes down, but doesn't quite go below the axis again. So in this case, you have only 1 real root. The other 2, which you have to make 3, are going to end up being complex roots. So what you might say, for instance, is that your real root is going to be x is equal to, like, let's say -3, 1 real root. And then the other 2 roots, 2 more complex roots. So in other words, when we learn how to solve these things, we might find out that the real root is -3, and the complex roots might be 1 plus I, that's a complex number, and then 1 minus I, that's another complex number, for a total of 3, right? And then one more quick case, since we're just trying to be, you know, explicit about everything, we might have something that looks like this. We might have the function go back, bend back below, and then go up like this. It's a similar kind of situation. You have 1 real root here, right? And you have 2 more roots that are complex, which we haven't learned how to solve yet, but they have to add up to equal 3. So 3 real roots, 3 roots total, only one of which is real. 3 roots total, only one of which is real. And we're only going to do one more here. We're going to talk a little bit about the quartic equations. The way you spell it is like this, quartic equations, right? And so the quartic equation looks like this. It's a 4th power, ax to the 4th, bx to the 3rd, cx squared, dx e. So I have to use different letters, right? And if you want to solve this quartic equation to figure out where the roots of it lie, then you just set this whole thing equal to 0. Ax to the 4th, bx to the 3rd, cx squared, dx plus e equals 0. Now we have no idea how to solve this. We haven't learned that yet. But there are methods and techniques you can learn to figure out the values of x. There's going to be 4 values of x that are going to make this thing equal 0. 4 solutions because it's a 4th power. That's what we expect. So in general, the quartic, which we kind of learned, we looked at in the demo there, in general is going to look like this. It's going to be a W of some kind. It's going to go down and up kind of like this. Right? Now, of course, it can be flipped upside down, so it can look like an M, right? But in general, it looks like a W. So in this case, you have 1, 2, 3, 4 crossing points. So you have 4 real solutions, like this. And then, of course, we have other possibilities. Let's take a look at some of them really quickly. What if we had the case, which we briefly did examine, something like this? It goes down, then up, but not quite high enough. And then it goes back up like this. We have only 1, 2 real solutions and 2 complex. We can't represent the complex solutions on this graph, but we know they have to exist because we know there has to be 4 total. And then we have the final case, which I want to talk to you about. And then we're basically almost to the end of all this stuff. The final case, if the quartic actually goes down, then up, then down, then up, but we never had any crossings at all, then we would have 4 complex solutions. Why have I gone through all of this stuff? The truth is we're not going to learn about quartic equations anytime soon. What we're really going to be doing is focusing on the quadratic equations. But oftentimes, I know when I first learned this stuff, I didn't understand why we were doing it. Why do we care? Well, it turns out that solving polynomials, these are all different kinds of polynomials, is really, really important. It has applications in calculus and physics and chemistry and engineering, because a lot of times, even when you're solving really complex equations, which are called differential equations in calculus, oftentimes it boils down to solving polynomial equations as part of the solution process. So we have to crawl before we walk, right? But this entire set of lessons is going to be focusing on the quadratic equations. So I want to give you an intuitive feel, because sometimes you're going to figure out that you do have the two solutions, and sometimes you're going to find out that you have two solutions that are real and two solutions in other cases that are complex. And I never really understood when I learned this the first time, when do you have the real solutions and when do you have the complex solutions? This is what it boils down to. Lines in general cross in one location. You're going to have one solution because the highest power of x is a 1. The quadratics are always going to have two solutions, but depending on where the graph is, those two solutions can be both real or both complex. Here we have two crossing points, so we have two real solutions. Here we have two crossing points, so we have two real solutions. Here we don't have any crossing points at all. We still have to have two solutions, but they're both complex. When you actually solve those polynomials that would give rise to these graphs, you'll find you're going to get, with quadratic formula, which we'll learn soon, you're going to find that you get imaginary or complex solutions. And then we have the cases where the graph just kisses the axis, and we talked about why these are double roots. They count as two roots as well for a total of 2. Then we have the cubic equations, which look like these snaky functions. Of course, remember, you can mirror image or reverse them so that they go up and then kind of down like this. In general, they'll cross in 3 locations, 3 roots for a power of 3. In this case, it doesn't look like there's 3 roots really, but there is, because there's 1 real root and then we have the 2 imaginary roots or complex roots that would make for a total of 3. Here in this case, we'd have 1 real root and then the other 2 would be imaginary or complex roots. And then we have the quartics, where in generally we have 4 crossing points, but depending on where the graph is, 2 of them might be real and 2 of them might be complex. So that's why when you're solving these equations, and we're going to be focusing on the quadratics, sometimes you'll get real, sometimes you get complex. What it means is if you were to graph those functions, that tells you what the graph really looks like. It tells you where the crossing points are, how many of them are there, and that's basically what it boils down to. And that's all I want to really get into now. So what we're going to do is we're going to be learning how to solve quadratic equations with new methods that you haven't learned before. They're among the most important topics and types of equations that we're going to learn how to solve, that have applications and everything. So we're going to spend a lot of time on it. So follow me through the next batch of lessons, and we'll be covering the solution methods for quadratic equations in great detail.